So this is Dr. Kavita Singh, Associate Professor, Department of Civil Engineering, Institute of Aeronautical Engineering. So today our topic will be energy interactions with atmosphere. So what happens when the energy interacts with the atmosphere, and what happens when the energy interacts through the atmosphere, and when it reaches, before it reaches to the ground surface, what happens, that we are going to learn today. So before we discuss this energy interactions with the atmosphere, let us go through the contents. What are the contents we are going to discuss today? So today we have this energy interactions with atmosphere, atmospheric windows, scattering mechanism, Rayleigh scattering, Mie scattering, Raman scattering, non-selective scattering, absorption. So these are all things we have to just understand when we talk about this energy interactions with the atmosphere. First of all, what is energy? So in the previous lecture, we have discussed about the energy, sun's energy, the electromagnetic energy. The electromagnetic energy, when it interacts through the space, and it has to pass through like many of the dust particles, many of the things which will absorb the energy, or many mechanisms will happen in the atmosphere itself before it reaches to the ground. So energy, electromagnetic radiation detected by remote sensor has to pass through the atmosphere twice. It has to pass through the atmosphere twice before and after it interacts with the Earth atmosphere. Twice in sense, if this is the sun, so electromagnetic radiation, whenever the sun is available, the radiation will be passing through the atmosphere. So this is the sun, while when it reaches to the ground, before it reaches to the ground surface, it has to pass through from the atmosphere. So this is the atmosphere where it passes through. So in the atmosphere, we will come across like different types of clouds will be there, dust particles will be there, gases will be present. So due to this dust particles, gases present in the atmosphere, the scattering mechanism will take place. So when it interacts with the atmosphere, so most of the gases, most of the radiations, either it scatters from its path or it absorbs. So depending on the dust particles or gases present in the atmosphere, the scattering or absorption happens in the atmosphere itself. Now, rest of the radiation, out of the 100% of the radiation, 50% of the radiation is either scattered, either absorbed. Then later, when it reaches to the ground, just 50% radiation only it reaches to the ground. So when it reaches to the ground, different types of features are present on the Earth surface features, like we have tree, water body, hills, mountains. So these all features, they reflect differently. So either they reflect, either they absorb, either they transmit, depending on the type of the feature it is having. So again it reflects back and goes back to the sensor. So satellite will capture this all energies. So while going back to the sensor, again it has to interact with the atmosphere. Okay. Again it has to interact with the atmosphere. That's why the atmosphere has to, it has to pass through atmosphere twice. So before and after. So this is before and this is after. So 2 times it has to interact with the atmosphere. This passage will alter the speed, frequency, intensity, spectral distribution and direction of the radiation. Now, as a result, atmospheric scattering and absorption will take place. First of all, before when it interacts, so what happens before? Scattering and absorption will be taking place. So scattering is deviating the light from the path. So what happens when a light fall on the surface or else in the atmosphere? So due to presence of the dust particles or due to presence of the water vapor, presence of the gases, so what happens is generally deviates the path. Like if the radiations are falling like this, so due to presence of dust particles or water vapor or gases present in the atmosphere, so it deviates the path of the radiation. So that's why the scattering will occur. Now absorption will occur when the gases are present. So most of the gases like carbon dioxide, ozone, so these are the gases which are, or water vapor, which are present in the atmosphere. They will absorb the radiation. So either it scatters, either it absorbs. So two mechanisms will take place when the energy interacts with the atmosphere, either scattering, either absorption. So these effects are most severe in the visible and infrared wavelength regions. So the range very crucial in the remote sensing. So this always happens in the visible region, either in the infrared region. So visible region, I hope you remember, we have discussed in the electromagnetic radiation, electromagnetic spectrum we have discussed. In the spectrum we have different regions here, like we have short wavelength region, and we have long wavelength region. So short wavelength and long wavelength region. So in the short wavelength region, always the absorption will take place. And in the visible region, this is the region where the radiation can pass through. So this is the visible region from where the radiation can pass through. Whereas in the long wavelength region, this is the active region. So in this region, generally we don't need the sunlight for the remote sensing purpose. So during the transmission of energy through the atmosphere, light interacts with gases, particulate matters in the process called atmospheric scattering. So the process called as atmospheric scattering. So during the transmission of energy through the atmosphere, light interacts with gases, particulate matter is the process called as atmospheric scattering. So this is how this image is like about the scattering. When the sunlight falls, so due to presence of the dust particles or some presence of the gases, either the scattering will take place. Scattering means deviating the light from its path. And due to the suspended particles present in the atmosphere, this will also deviate the path of the electromagnetic radiation. So here in this image, we can just see out of the, it's like how much percentage of the radiation comes from the sunlight. So if it is 100%, we say if it is 100% of the radiation, it is passing through the sunlight. So that 100% of the radiation will not reach the Earth's surface. So what happens when 100% of the radiation, when it falls on the ground, so what happens? 6% of the radiation is reflected by the atmosphere. Okay, 20% of the radiation is reflected by the clouds, reflected from the Earth's surface, and 4% is reflected from the Earth's surface, right? And rest absorbed by the land and oceans. 51% is absorbed by the land and the oceans. When it reflects back again, conduction and rising air 7%, absorption by the clouds again 33%, absorption by the atmosphere 16%, radiated to the space from the clouds and the atmosphere 64%. So out of the 100%, returns back as 64% or 6% through radiate directly to the space from the Earth. So this is energy interaction when it falls on the Earth's surface, when it interacts with the atmosphere. This is what happens due to presence of dust particles or presence of cloud or water vapor in the atmosphere. Now coming to this atmospheric windows. So what is atmospheric windows? Now the scattering mechanism will take place, either absorption will take place. So atmospheric window generally we talk about when we see this electromagnetic spectrum, like we have here short wavelength and we have here long wavelength. Okay, short wavelength, long wavelength. Now in this portion we have one more division called as visible region. Okay, visible region. We have short wavelength region. This is one region. This is a visible region. And this is long wavelength region. So the short wavelength region, we have ultraviolet region, X-ray region, gamma ray region. So these all regions which are in short wavelength region, they will absorb the heat. They will absorb the radiation. they will not allow the radiation to pass through. So this region is totally waste for the remote sensing. Now, when we talk about this visible region, which ranges from 0.4 to 0.7 nanometers, so this visible region is only possible for the passive remote sensing. Passive remote sensing. So in this region itself, the electromagnetic radiations are allowed to fall to the ground. Okay. So in this region itself, it is possible that electromagnetic radiation can pass through it and reaches to the ground. So this visible region is only possible for the passive remote sensing. Passive remote sensing. Okay. So this passive remote sensing is possible through the visible region. So because this is the window from where the radiation will pass through, that's the reason it is called as atmospheric windows. It is called as atmospheric windows. Okay, it is a window in the atmosphere from where the energy radiations will pass through. Nothing will interrupt in between. So whatever radiation is present over here, it will pass through and reaches to the ground. So that's the reason it is called as atmospheric windows. So while passing through the atmosphere, electromagnetic radiation is scattered, absorbed by the gas particulates. Beside major gases components like molecular nitrogen, oxygen, other constituents like water vapor, methane, hydrogen, helium, nitrogen compounds play an important role in modifying the incident radiation and reflected radiation. So the regions of electromagnetic spectrum in which the atmosphere is transparent is called as atmospheric window. That means it is a transparent atmosphere where there is no scattering, there is no absorption. This is only the window where electromagnetic energy can pass through it. That's why it is called as atmospheric windows. Now the atmosphere is practically transparent in visible region of the electromagnetic spectrum. Therefore, many of the satellite-based remote sensing sensors are designed to collect data in this region. Now, some of the commonly used atmospheric windows are 0.38 to 0.72 nanometer, the visible region, or 0.72 to 3 nanometer near infrared and middle infrared, and 8 to 14 nanometer thermal infrared. So these are the regions we generally call it as atmospheric window from where the energy can pass through it, and then it is possible for the passive remote sensing. Passive remote sensing. Okay. It is possible for passive remote sensing. Right. Now this is how it looks like. This is our incoming radiation, and this is our electromagnetic spectrum. Electromagnetic spectrum. So in this spectrum we have this region called as visible. Okay. So this visible region is only called as the atmospheric window from where the radiations can pass through and reaches to the ground. Now, generally what happens when it interacts with the atmosphere, as we have discussed in the previous slide, two mechanisms happens. One is scattering and other one is absorption. So when the scattering happens, so to major process in the scattering, so when it happens, there are different types of scattering it will take place. So different type of scattering we have selective and non-selective. So under selective we have Rayleigh scattering, Mie scattering and Raman scattering. So these all scattering will take place when it interacts with the atmosphere. So let us see about this table. In this table we have Rayleigh means smaller than the wavelength, and the particle size will be smaller than the wavelength. So suppose this is the particle size and this is the wavelength. So particle size will be the smaller than the wavelength, then this Rayleigh scattering occurs, and the type of effective atmospheric particles are gas molecules. Scatter of particles are molecule absorbs, high energy radiation re-emits, skylight scatter, inversely proportional to power of wavelength. And effect of scattering on the visible and near visible wavelength. affect short wavelength, visible wavelength, resulting in haze, photography, and blue skies. So why do we see the blue sky is due to this Rayleigh scattering. Like that, we have Mie scattering, same size as the particle of the wave. Same size means it is same size as the particle, and radiation and spherical particles, fumes, and dust. Physical scattering under overcast skies affects all visible wavelengths. Non-selective, larger than the wavelength of radiation. So water droplets and dust. Physical scattering of fog and clouds after all visible wavelengths equally resulting, while this fog and clouds will be result of this kind of scattering. Now Raman scattering is any. So photons and elastic collision with molecule resulting in loss of gain in energy. This can decrease or increase in the wavelength. So this is about overall scattering. Size effective of atmospheric particles, whether the type effective in the atmospheric particles, scatter of the particles, effect of the scatter on visible and near visible wavelength regions. Now one by one let us see what is it. So Rayleigh scattering applies to the particle that are small with respect to the wavelengths of light. So it's like just now we have discussed. So if the particle size applies smaller than the wavelength. Suppose this is the wavelength, so particle size will be the smaller than the wavelength. And the Rayleigh scattering is phenomenon where small particles or molecules at the atmosphere scatter sunlight, causing it to spread out to appear blue. So some examples of Rayleigh scattering is like blue sky. Why the blue sky occurs? So one of the most familiar example of Rayleigh scattering is the blue color of the sky. Why we can see the sky as blue is due to this Rayleigh scattering. So the Earth atmosphere contains molecules such as nitrogen and oxygen, which are much smaller than the wavelength. So Rayleigh scattering occurs when the particle size will be smaller than the wavelength. Then only this Rayleigh scattering will occur. And wavelength visible light. When sunlight enters the atmosphere, these molecules scatter shorter blue wavelengths more effectively than longer red wavelengths. As a result, we can see sky blue during the daytime. So this is why happens when the molecules scatter shorter blue wavelength more effectively than the longer red wavelengths. That's the reason our eyes can see sky as blue in color due to this Rayleigh scattering. Now the next example we can see sunset and sunrise colors. During sunrise and sunset, the sun is lower on the horizon and sunlight must pass through a thicker layer of the Earth atmosphere to reach the observer's eye. So this increased path length leads to more scattering of shorter blue and green wavelengths. So this allows the longer red and orange wavelengths to dominate. This will allow the longer wavelength to dominate. That's why the sky's color we can see at the time of sunset and the sunset and sunrise, that will be red color and orange color. So this is why the sky appears red, orange or pink during the sunrise and the sunset. So this is because of Rayleigh scattering. Now this third example we can see here, haze and smog. So particles in the atmosphere such as dust, pollution, aerosols can also scatter sunlight through Rayleigh scattering. So this scattering can lead to reduced visibility, whitish appearance in the atmosphere, particularly in the areas with high levels of air pollution or haze. And next example what we can see is blue color of water bodies. Why the blue color is appeared in the photos and why our eyes can see the water as blue is due to this Rayleigh scattering. Like Rayleigh scattering also occurs in the water bodies of water. The blue color of oceans, lakes, rivers is partially due to scattering of shorter blue wavelengths by water molecules, similar to scattering of sunlight in the atmosphere. So these examples illustrate how Rayleigh scattering affects the appearance of sky and other atmospheric phenomena, contributing to the colors we observe in the nature. So this is all because of the Rayleigh scattering. Now coming to this Mie scattering. So Mie scattering named after the German physicist Gustav Mie. So this is named after the physicist of Gustav Mie and is the phenomenon where particle in the atmosphere scatter sunlight, typically when these particles are larger the wavelengths of the visible light. Now previous one we have seen the particle size was the smaller than the wavelength. Now here the particle size will be the bigger and the wavelength size will be the smaller. So that's why this mice scattering will occur. Whereas in the Rayleigh scattering, we have seen particle size is smaller than the wavelength, while as in mice scattering, the particle size will be the larger than the wavelength. Unlike Rayleigh scattering, which primarily affects shorter wavelength of light, such as blue and violet. Now, a few examples we can see here. Clouds. Clouds consist of tiny water droplets or ice crystals suspended in the atmosphere. These particles are large enough to cause mice scattering of sunlight. So cloud appear white or grey because they scatter sunlight of all colors equally due to mice scattering. That's the reason the cloud appears white or grey because they scatter sunlight of all colors equally due to the mice scattering. Now, due to the mice scattering, these clouds appear in the grey color. Now, fog. Fog consists of tiny water droplets suspended in lower layers of atmosphere. Similar to clouds, fog particles scatter sunlight through mice scattering, leading to reduced visibility characteristics and greyish appearance of foggy conditions. So, fog also it appears in grey because of this mice scattering only. Now we have haze. Haze is caused by suspended particles such as dust, smoke, pollution in the atmosphere. So these particles are larger than air molecules and they scatter sunlight through mice scattering. So haze can reduce the visibility and cause a whitish or grayish appearance in the atmosphere. So haze can reduce the visibility and cause the whitish or grayish appearance in the atmosphere, and this happens due to this mice scattering. Okay. Now we have rainbows and halos. So mice scattering can also contribute to the formation of rainbows and atmospheric halos. So raindrops of ice crystals in the atmosphere scatter and reflect sunlight, leading to the formation of the rainbows. So why our eyes can see rainbows? Due to this mice scattering. So it's like mice scattering can also contribute to the formation of the rainbows and atmospheric halos. Raindrops or ice crystals in the atmosphere, they scatter and reflect the sunlight. Leading to the formation of the rainbows and halos around the sun or moon. So the size and the shape of the water droplets or ice crystals influence the appearance of this optical phenomena. That's why our eyes can see the rainbows due to this mice scattering in the atmosphere. Now coming to the Raman scattering. So the Raman scattering is not that much important here. Like Raman scattering named after the Indian physicist called as C.V. Raman. Physicist C.V. Raman, who discovered in 1928. And is a phenomenon in which energy of incident photons is changed due to the interaction with the vibrational or rotational modes of the molecules. So it's like incident photons and it will change due to the interaction with the vibrational and rotational modes of the molecule. Now, unlike Rayleigh scattering and mice scattering, which involve elastic scattering, no change in the energy. Elastic scattering, these are elastic scattering which don't have any change in the energy. Whereas Raman scattering involves in inelastic scattering. Rayleigh scattering occurs, mice scattering will involve elastic scattering, whereas Raman scattering will involve inelastic scattering, where the energy of scattered photons differ from that of the incident photons. Now, like here are some aspects and examples of Raman scattering, like Stokes and anti-Stokes shift. In Raman scattering, incident photons interact with molecules in the sample and they cause them to undergo energy transitions. So Stokes scattering occurs when scattered photons have less energy and the incident photons, while anti-Stokes scattering occurs when scattered photons have more energy. So that is high frequency, more energy is high frequency, less energy is low frequency. So when scattered photons have less energy, then it is called as low frequency than the incident photons. And when it is having a high frequency, then it is having a more energy than the incident photons. Now we have Raman spectroscopy. Raman spectroscopy. So Raman spectroscopy is a technique that utilizes Raman scattering to analyze the vibrational and rotational modes of molecules in the sample. So by measuring the energy shifts, Stokes and anti-Stokes shifts of the scattered photons, Raman spectroscopy provides valuable information about the chemical composition, structure, bonding, properties of the materials, and it is widely used in the chemistry, material science, biology, pharmaceuticals, and forensic analysis. Now, some more applications we can see. Biomedical applications like Raman spectroscopy has applications in biomedical research and medical diagnostics, and it can be used to analyze biological samples such as cells, tissues, and bodily fluids, providing valuable information about disease states, drug interactions, and molecular mechanisms. So it has an application in the biomedical field where it analyzes the biomedical samples like cells, tissues, and it gives a valuable information about the disease and drug interactions and the molecular mechanisms. So it has a good application in the biomedical field. Now we have a material characterization. So Raman spectroscopy is valuable for characterizing the properties of materials such as polymers, ceramics, semiconductors, and nanomaterials. Okay, so Raman spectroscopy is valuable for characterizing the properties of materials, polymers, semiconductors, and nanomaterials. So it can identify chemical compositions. Crystal structures, and defects in the material, aiding in the development of new materials and quality control process in manufacturing field. Okay. Now when we talk about this non-selective scattering, so here scattering mechanism is not in the Raman. It is only scattering mechanism we see in the Rayleigh scattering, Mie scattering, and non-selective scattering are the important scattering mechanisms. Now coming to this non-selective scattering mechanism. So non-selective scattering refers to the scattering process in which all wavelengths of the incident light are scattered equally. That means the particle size and the wavelength size will be equal. Okay, it will be equal to the wavelength. So without any preference for the particular wavelength or colors. So this non-selective scattering, always the wavelength and the particle size will be equal. So unlike selective scattering process such as Rayleigh scattering, Mie scattering, or Raman scattering, where certain wavelengths are preferentially scattered due to specific physical mechanisms. So non-selective scattering results in uniform scattering across the entire spectrum of incident light. So non-selective scattering results in the uniform scattering across the entire spectrum of incident light, like because it has the scattering mechanism, and it is like when it happens when the particle size and the wavelength size is equal to the wavelength. Both are equal. So it happens equally. Incident light are scattered equally. Next, non-selective scattering can occur due to various factors. Why it occurs? Due to various factors. So what are the factors here? We'll see. We have large particles present over here. So when particles or droplets in scattering medium are much larger than the wavelength of the incident light, they may scatter light in a non-selective manner. So whenever the droplets, the particles or the water droplets are present in the atmosphere, so the incident light, they may scatter light in non-selective manner. These particles may scatter light in all directions with little or no dependence on wavelength, resulting in the uniform scattering across the spectrum. Now, a high concentration of the scatterers. So, in densely packed scattering media, such as colloidal suspension, highly turbid liquids, presence of numerous scatterers can lead to non-selective scattering. Like when in a dense packed scattering media, such as colloidal suspensions and some turbid liquids, and presence of numerous scatterers can lead to the non-selective scattering. And the sheer number of scatterers ensures the incident light is scattered in all directions and across all wavelengths, leading to uniform scattering. Now we have the complex or irregular surfaces. So surfaces with complex or irregular geometries may scatter light in a non-selective manner. Irregularities on surface can cause light to be scattered diffusely in all directions, resulting in non-selective scattering. These are some examples of why the scattering mechanism happens. Now, till now we have discussed about the scattering mechanism. So when the energy interacts with the atmosphere, the scattering and absorption happens. So we have discussed about the scattering mechanism. So in the scattering mechanism, we have seen that this electromagnetic radiations will be scattered, or it will be deviated from the path due to presence of water vapor, due to presence of dust particles, due to presence of huge particles in the atmosphere. It deviates from its path. So why the sky appears blue, why the water appears blue in color, why the sky appears gray in color, so why the sunset and sunlight appears, sunset and sunrise appears red and orange in color. So due to this all scattering mechanism, our eyes are able to see these colors in the atmosphere. So this is about the scattering. Now we'll talk about the absorption. So now what is absorption? Because the two mechanisms will take place. One is scattering, other one is the absorption. So scattering we have already discussed. Now coming to the absorption. So absorption when happens? When the lot of gases, the presence in the atmosphere, some greenhouse gases which are present in the atmosphere, they will absorb the heat. They will absorb the electromagnetic radiation. So a lot of absorption occurs. That's the reason when the radiation is falling on the earth's surface, when it passes through the atmosphere, most of the radiation will be absorbed by these gases. So is the other main mechanism at work when electromagnetic radiation interacts with the atmosphere. When the electromagnetic radiation interacts with the atmosphere, in contrast to scattering, this phenomenon causes molecules in the atmosphere to absorb energy at various wavelengths. Ozone, carbon dioxide, water vapor are three main atmospheric constituents which absorb the radiation. So when these gases which are present in the atmosphere, and these are all greenhouse gases, which are present in the atmosphere, and this will absorb the radiation when it falls, when it come across to the atmosphere. So what is ozone? So ozone is a layer in the atmosphere which absorbs the very harmful UV radiations. So ozone, when it is in atmosphere, it is absorbing the UV radiations, but once the ozone reaches to the ground surface, it is very much harmful to our environment. So absorbs and harmful UV radiations from sun. Without these protective layer in the atmosphere, our skin would be burned and exposed to the sunlight. So this protective layer, like we have a ozone layer in the stratosphere. So this layer will help the ultraviolet radiation to absorb the radiations there itself, and it will not allow this ultraviolet radiation to reach to the ground surface. So that's how the absorption will take place due to presence of the ozone layer. Now we have carbon dioxide. So carbon dioxide is a greenhouse gas. And this is because to tend to absorb radiation strongly in the infrared portion of the spectrum, that area associated with thermal heating, which serves to trap heat. So it has a like carbon dioxide always takes a greenhouse gas, and it will be always trapping the heat. So wherever the carbon dioxide presence is more, so that area will be under the heat conditions, like it has a capability of trapping most of the heat in the atmosphere. So when this carbon dioxide is present in the atmosphere, it will absorb the radiation in the infrared portion of the spectrum and the area associated with the thermal heating, which serves the trap heat in the side in the atmosphere. Now we have the other gas present in the atmosphere called as water vapor. So what does the water vapor do? So water vapor in the atmosphere absorbs much of the incoming long wave radiation, infrared and short wave, microwave radiation. So this will absorb lot of incoming and outgoing radiations from the microwave region. So that's how this ozone, carbon dioxide and water vapor, these are all gases which absorb the heat in the atmosphere itself. So when the energy interacts, either the scattering mechanism happens, either the absorption will take place. The absorption will take place when these gases are present in the atmosphere. Because these gases absorb electromagnetic energy in the very specific region of the spectrum, so those areas of the spectrum which are not severely influenced by atmospheric absorption and thus are useful for remote sensors. So previously also we have discussed the atmospheric window where the electromagnetic radiation will be not influenced by the absorption or scattering. So that areas are only useful for our remote sensors, that too for the passive remote sensors when it falls in the atmosphere. So this is the two mechanism will happen when the energy interacts with the atmosphere, right? So I hope you understood what is scattering and what is absorption and why it happens, why our eyes can see the sky blue in color, why our eyes can see the water body in blue in color. So these are all due to our Rayleigh scattering, Mie scattering, non-selective scattering. We can see these all colors by our eyes in the atmosphere, why the rainbow occurs. So these are the scattering mechanisms. Due to that only we can see these all rainbows in the atmosphere. Okay, so these are some references where we can go through and just understand more content about this scattering mechanism or absorption mechanism with the energy interacts with the atmosphere. Like we have a book called as M. Anjireddy. Dr. M. Anjireddy, he is the author of the book, and he has written the book as Remote Sensing GIS. It is from the BS Publications, New Delhi. So it is having this all contents in this book. You can just go through and find out the more information about the scattering and the absorption process. Now we have one more book called as Fundamentals of Remote Sensing by George Joseph. It is from the University Press, Hyderabad. And the other one we have IARE Narayana. This is for remote sensing and its applications. And this is also from the University Press. You can just go through about remote sensing and applications. Like if you want to know about more application part, you can just go through this book. Now we have Esquire Basics of Remote Sensing and GIS. And this is also one of the good book where you can just get the content about this scattering mechanisms and remote sensing process. Now we have one more book called as Tang Chan. So this Tang Chan book, it is about the GIS, which gives you the total GIS information, the entire GIS mechanism, how it works, how the process will go on. This is a very good book for the GIS process. You can just go through if you want. And Remote Sensing GIS by B. Bhatta is also one of the book. You can just go through these references. These are all references you can just go through. Just find out the more content about this scattering mechanism and absorption mechanism. So that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.